Amplitude amplification is a generalization of Grover's search problem. In it, you are given an initial state and an oracle function that marks some elements of a set, B. Rho denotes the probability of finding a marked state if psi is measured, and is related to the angle alpha. We can define an operator Q, which, when applied to the state, increases the angle by 2 alpha. In the standard algorithm, Q is applied k times, and then the state is measured. This k is decided beforehand, setting it to a value that maximizes the probability of success. We argue there's a different option. Do not apply Q a fixed number of times, but instead test a condition after every application of Q. If and only if the condition is met, the algorithm stops, as if it were a while loop. But can we test a condition on a quantum state without destroying the quantum speedup? Perhaps surprisingly, yes we can, if we use weak measurements. These are measurements that disturb the state just slightly, but in turn provide little information. In order to apply a weak measurement on H, we need an auxiliary space P. P is known as the probe, and it has a chosen orthonormal basis, 0, 1. With the probe initially at 0, we use unitary E to entangle the state with the probe. E is parameterized by kappa, which determines the strength of the correlation created. Then we measure only the probe, and thanks to the correlation, we'll learn a bit about the state. With some small probability, we may read 1 when measuring the probe. In that case, we automatically succeed in finding a marked element. Otherwise, we read 0 from the probe, and the angle is decreased an amount dependent on kappa, which we can calculate using trigonometry. Assuming kappa is small enough, the collapse due to the measurement is overcome. We prove that for kappa smaller or equal to square root of rho, the angle is increased by at least alpha on each iteration. Then, it is easy to check that for roughly half of the iterations, the probability of success is greater than kappa over 2. The algorithm succeeds as soon as the probe reads 1, so the success probability follows a geometric distribution. The expected value of this distribution is 4 over kappa. If we set kappa equal to square root of rho, we get the same query complexity as the standard amplitude amplification algorithm. We later found out a paper from 2008 proposing essentially the same algorithm as ours, although they do not discuss it from the perspective of while loops and weak measurements, as we do. We've also found out that our weak measurements could be replaced by a procedure that tosses a classical coin and only measures when it's heads. This has the same query complexity as our proposed algorithm. Finally, as further work, we'd like to rephrase our algorithm in the continuous time setting. If the quadratic speedup is maintained in the presence of a continuous, uninterrupted measurement on the probe, this might provide a new approach for the experimental realization of amplitude amplification.